Okay, so as you can see here, C2H6O, it can exist in two forms, that is alcohol and ether. So that is nothing but isomerism. So when we want to systematically study isomerism, so these isomers, right? These isomers are of different types. The first division is actually based on, right? First division is we say there can be a structural isomer or stereoisomers. So what does structural means? Structural isomers are also called constitutional isomers sometimes, but mostly the term which will be used will be structural isomers. Now, the example which you saw above is an example of structural isomer. You can see the entire structure is different. The structure of the compound itself is, or the molecule itself is different, two different molecules. So that is called structural isomer. And obviously the structure will be different. It will have different name. So how to identify whether the isomer is structural isomer or not? It will have different name. IUPAC name will be different. The above example, one is alcohol, other is ether, and obviously it will have different attachment. So the group which is attached, or the branching, or even the structure, these things will be different. So that is called a structural isomer. Now in structural isomers itself, you will find different varieties or different classification in structural isomers as well. So you have structural isomers, in that there is chain isomerism, then there is positional. We will study them one by one. Just get to know the name first. Positional, then we have functional, and you have metamer. We will study this in detail later. And you also have tautomers. So these are the the structural isomers. So there are 5 types of structural isomers. So example we have seen above. One of the example is above. Now coming to the stereoisomer. Stereoisomers should be different from structure. That means they won't have different name. They won't have different structure. They won't have different attachment. That means they will have same name, same attachment, same structure. Then what will be the difference? Difference will be in physical and chemical property. So the question comes, if they have everything same, molecular formula same, structure same, attachment same, name same, then why will be there any difference in their properties? The answer is, say for example, if a compound is like this, right? Or it may have a different orientation. So if you see these two compounds, they will have same name, right? Both of these will have same name. What will be the name? 1, 2, 3, 4. So it is but 2-ene. Both of them will have same name. So that means their structure is same, their attachment, structure, name, everything is same. Then why will be there any difference? So that is what we are going to study in stereoisomers. So the main thing which we see here is that they have same name, structure, but they have, if you see the above example, they have different orientation. Orientation is different. This methyl and this methyl, CH3, CH3, they are on the same side of double bond, while here they are on the transverse side of double bond. So that is nothing but orientation. There is no difference in structure or the attachment, but orientation is different. So they have different orientation in space. So that is the main differentiating factor. Now, what is the reason for this? Why there is different orientation? So this is due to the restriction in a multiple bond towards rotation. What does that mean? See, if you have a double bond, we know that double bond actually means what? Double bond is a combination of, or it is actually a sigma plus pi bond. So if there is a sigma bond, so let's say pp sigma bond, so it will look like this. So this is p orbital, this is p orbital, this is how the sigma bond will be formed. Sigma bond is always axial overlapping. So now what happens here is if it wants to rotate about this axis, this rotation is possible, right? Say for example, if you have C, so here rotation about this axis is possible. But if it is a double bond, in double bond, what do we have? In double bond, we have, say for example, if we take PP, right? So there will be a sigma bond, and apart from that sigma bond, there will also be a pi bond. So even between these orbitals also there is a bond. And now if it wants, if you observe this, right, here rotation is not allowed. There is a restriction on rotation. This rotation is not possible. So what does that mean? See, if you take this example, suppose if there is a Cl there instead of H, there is a Cl. So what can happen is, this is one form, but this rotation is possible, and it can change its form from one form to another, from one orientation to another orientation. It can change, and it will always go back and settle at the most stable orientation. That is here, when there is only sigma bond. But here that is not possible. What does that mean? That means that, for example, here, if it settles in this orientation, from this orientation to this orientation, or from second to first or first to right, this is possible only if there is rotation. But because of double bond, rotation is not possible. So this is a separate entity. First one is a separate entity, and second one is a separate entity. They both exist. And obviously, they will have different properties. Now, question comes, why they will have different properties? So let's see that example as well. So for example, again, you have this here C. So let's say here and here you have HCl, and here Cl and H. And another possibility is what? C, double bond C, H, H, and Cl, Cl. So if you see in the first one, the distance between Cl and Cl, the distance between Cl and Cl is more, while here they are on the same side. So you can assume it to be like this, while here in the first case it is like this. So repulsion between Cl will be less in first, while repulsion between Cl will be more in second. So obviously, due to this internal repulsion, which is more and less, in one it is more, in one of the structures it is more, in another structure it is less. So due to that, obviously it will have different behavior. There will be difference in behavior due to difference in orientation. Structure is same, name is same, attachments are same. There is no difference. So your IUPAC name will also be same for both of them, but its behavior, its chemical and physical properties will be different. Why different? Because of difference in orientation. Why there is a difference in orientation? Because of restriction in multiple bonds. So these two structures, not structures, these two orientations which you see here, they are not interchangeable. They both exist. They both are two separate entities having different properties. So these isomers are called stereoisomers. Right now, just like structural isomers, sorry. Just like structural isomers we have seen, they are of they are of 5 different types. The stereoisomers are again divided into 2 categories. First, 2 categories. What are those 2 categories? So this is stereoisomers. So that is divided into 2 categories. First is configurational, and the second one is conformational. Right? So what is the difference between configurational and conformational? Let's study that. So configurational isomers are isomers which can be isolated or separated. So if you have a mixture of these isomers, they can be isolated or separated by some physical or chemical methods or means. Right? So obviously that means here they cannot be separated. Right? So actually these isomers, conformational isomers, they are sometimes also called not true isomers. So the reason is why they cannot be separated. That is possible only if there is no physical or chemical way to distinguish them. That means they cannot be distinguished by chemical or physical methods. That means chemically and physically they are same. But still there is some difference in orientation. That's why they are called conformational isomers. They are treated as isomers, but they are not true isomers. Right? So they are mainly due to sigma bond or single bond rotation. So we will study them as well. Okay. So these are the, you can say 5 plus 2, total 7 major isomeric forms or types of isomers. Chain, positional, functional, metamer, tautomer, they are the structural isomers, and configurational and conformational, they are stereoisomers. Configurationals are in the stereoisomers, there will be change only in the orientation, and configurational can be isolated or separated. Conformational cannot be isolated or separated. So this was you can say a broader picture of isomers, right? In configurational, what you will see in configuration, let's see that as well. Configurational is again divided into 2. that is two different types of isomers in configurational as well. One is called geometrical or geometric isomers, and the next category is optical. So we'll study this. Both are very important. So the geometrical isomers are the simple isomers, that is that comes into existence due to multiple bond restriction, which we have already seen above, right? And this will be again here. There will be two types of configuration of any molecule. Same molecule, but two types. Same molecule, same structure, but two different types of configuration due to the restriction in multiple bond. What does that mean? That means the example which we have already seen. This. So if you have these two on the same side of multiple bond, and other possibility is what? They may be on two different sides or transverse side. So this one, the first one, this configuration is called cis configuration, and the second configuration is called trans configuration. So as you can see, we are not saying that they'll have two different names, only their configuration will be given two different names, cis and trans. Trans, in which they are on the opposite side, cis, in which the attachment is on the same side. So that is the geometrical isomer. Now the question is, what is optical isomer? So optical isomers are the isomers which are say same structure, same molecule, but having different behavior towards the PPL. PPL is plane polarized light. You must have studied this in optics, in physics. Polarized light, we will study that in detail. What is that? Later. So they have the two orientations when they have different behavior towards the plane polarized light. The two those two candidates or those two orientations are called optical isomers. So what is the different behavior? So this plane polarized light, when passes through one of them, will turn the light to left and other will turn it to right. That is the only behavior difference. We'll study this in detail later. Polarized light is a light which moves in a single direction. So suppose this light moves in a single direction, that is called plane polarized. Generally what happens to light? Light travels in all directions. Plane polarized light is in which the disturbance is only in one direction. So, and then if suppose sample A comes and it turns the light towards one direction, and if sample B comes and it turns towards the opposite direction, this is what is, then A and B will be called optical isomers if they have same molecular formula, same molecular structure, but this behavior. Is it clear what is optical isomer?
Yeah. So they have chiral carbon and
achiral carbon.
And
yes.
rotates.
Yes, exactly. So we'll see that. We'll see that in detail later when we'll study haloalkanes and other compounds. We'll study that in detail. But the basic mechanism of optical isomerism we'll study in detail here itself, in this chapter itself, so that when we come to the chapter where it is used, there we'll have to just revise it. Okay, so that was about optical isomer configuration. So configurational has two parts, geometrical and two types, geometrical and optical. Then what is left? Conformational. Conformational, as I said earlier also, it is not a true isomer. What we actually see here is somewhere I have written that it is due to sigma bond rotation. You have two different orientations, right? So say for example, if you have a structure like this, so there is carbon here, there is carbon here, and these can be any groups, the three. And as you can see here, you can see that one carbon is it's in 3D. I hope it is clear to you, right? And this is one configuration, and another configuration, not configuration, another orientation can be this. Right? Let's say this is orientation A, this is orientation B. This is, you are seeing a side view, not exactly side view, but at an angle. If you see it from the front, that is, if you see it from this side, then the same A and B will look something, will look little different. If you see A from this side, right, then what you will see is something like this, right? This will be, so the front one, let's say this is the front one and this is the back one. So they will be eclipsed by each other. That means the back one will not be visible. It will be like this. The one in the back will be hidden. Do you agree?
Yeah.
That is, if you see it from this side. But if you see the second one, the orientation B, from the front, it will look like this. This is the front one, and the back one will be like this. Is it right?
Yeah, I think it would.
Correct. So this thing is, this configuration, this is just the rotation of sigma bond. And we know that sigma bonds, the rotation about sigma bond is easier and it is unrestricted. This rotation about sigma bond is possible. It is not like the double bond or triple bond. So what happens here is, if this configuration is unstable, it will move to this configuration. If this configuration is unstable, it will move to this configuration. So it's not like they, both of them, it's not like from A form it won't change. A form and B form are not individual entities, independent entities. They are interchangeable. So only one of them exists, only one of them will be stable. So only one of them will exist more. Right? So this is not an isomerism is when both of them exist. Both of them are valid structures, both of them are valid orientations, and they both have their own stability. But here only one of them will be stable. It's not like both of them will be stable. It depends whether there is repulsion here. So if there is a repulsion here, it will change to the other form. Right? This is called conformational isomers. The one which you see in the first one is called eclipse. I hope you understood why it is called eclipse. And the second one is called scattered. So first one is called eclipse because the groups are being eclipsed. one group covers the group in the front, covers the group in the back. While in the second one, it is scattered because it is scattered.
Okay.
Right? So in total, now if you see, these are all the types of isomers. Chain, position, functional, metamer, tautomer are the structural isomers, and then comes stereo. Stereo is divided into configurational and conformational. Configuration has geometrical and optical. Geometrical, you will see cis and trans. Optical, you will see the behavior towards the light. One rotates the light towards left, and another rotate towards the right. So that will be the difference. And in conformational, we have seen that these are not true isomers because they don't exist in two different and independent forms, but in interchangeable form. One of them will be mostly eclipsed, will be less stable, and scattered will be more stable. So they interchange, and that's why these are not true isomers. So these are the total or different types of isomers which you will see, right? So if there is a sigma bond rotation involved, it is conformational. If there is a pi bond restriction, then that is geometrical. And if there is a light involved, then that is plane polarized light involved, then that is optical isomers. So these are the three different types of isomers in stereoisomers. Clear?
Yes.
Let's now move to these isomers, and let's now move to studying these isomers in detail. Let's start with the first one, that is chain isomers. So what exactly are chain isomers? So one thing is something which we already know, that it is a structural isomer. So these are the structural isomers first. And then what is the difference between two different structures? They differ in main chain or side chain. If that is different, then that is a chain isomer. So main thing is this, either the main chain will be different or the side chain will be different. That means what? If you see the IUPAC name, right? We have seen that every IUPAC name will have total 5 parts. That is secondary prefix, primary prefix, the root word, then the primary suffix and secondary suffix. So if the main chain itself is different, then what will change? It will be the root word which will be different. Right? Let's see an example. Let's say you have a molecular formula given C4H10. Simple. So C4H10, 10 is equals to 2 into 4 plus 2. It's clear that the degree of unsaturation here is 0. That means there won't be any double bond or any ring. Now, if you have to draw different structures, we have seen how you can draw it. You should start drawing carbon skeleton first in decreasing order. So first, let's draw this. So main chain with 4 carbon. That's all. There is no other possibility. Next is go for 3 carbon chain. So is 3 carbon chain possible? Answer is yes. This is the 3 carbon chain. Now, if you see, the formula is same for both. This is also C4H10. This is also C4H10. You can count carbon 1, carbon 2, carbon 3, carbon 4, C4. Then here, there are 3 hydrogen, 3 hydrogen, 3 hydrogen, and 1 hydrogen. So total 3 into 3, 9 plus 1, 10 hydrogen. So this is CH C4H10. But if you write the name of these compounds, this is normal butane, but this one is 2-methyl propane. Is that correct?
Wait. Yeah.
Right. So what you can see here is you have, from the diagram itself, it should be clear that the structure is different, and main chain has 4-carbon chain, and here the main chain has, it is actually a 3-carbon main chain. So the main chain is different. That's why these two are chain isomers. I hope that is clear, right? So let's see one more example of chain isomers so that you are comfortable. Let's take C5H12. So again, it will be similar. C5H12. Again, degree of unsaturation 0. Let's start writing the skeleton. So 5-carbon skeleton looks like this. 1, 2, 3, 4, and 5-carbon skeleton. Then next 4-carbon skeleton. Can we draw 4-carbon skeleton and have 5 C5H12? Let's see this. So this is a 4-carbon skeleton, and then you can add one more carbon here. So it is the main chain still has 4-carbon. So this is a 4-carbon skeleton. This is 5-carbon skeleton, and you can also have a 3-carbon skeleton. So you have only 3 carbon in the main chain. Can we still get 5 carbon in the whole molecule? Answer is yes. So now main chain has 3 carbon, but the entire molecule has 5 carbon. If you see the first one, formula is C5H12. You can count it. 3 here, 3 here, 2, 2, and 2. So 6 plus 6, 12, correct? Similarly here, 3, 3, 2, here also 3. I'm counting hydrogens because carbon, I don't think there is any doubt that there are 5 carbon. If you count the hydrogen, 3, 3, 3, 2, and there is one more here. Right? So that is total 12. So this is also C5H12. Similarly here, there will be 3 here, 3 here, 3 here, and 3 here, hydrogen. So even that is C5H12. So what we see here, they have same molecular formula, C5H12, but the main chain length is 5 carbon, 4 carbon, and 3 carbon. So these are also chain isomers. The main chain length is same, different, but the molecular formula is same. Okay, and obviously the name of the different molecules will also be different. This is pentane. This is 2-methyl pentane. Sorry, 2-methyl butane. It is a 4-carbon chain. So 2-methyl butane. Yeah. This is 2,2 dimethyl propane. So what do we observe here? The main chain or the root word is different in all the 3 compounds. If root word is same, then they are not chain isomers. That is, if the main chain length is same and even the side chain length is same, then they are not chain isomers. They are a different type of isomers. We will see that. Okay, so I hope this is clear. That is what exactly is chain isomer. Now let's move to the next type of isomer, next type of structural isomer, that is called positional isomer. So it should give you an idea. The position will be different, but position of what? Right? So first is that the first thing, there won't be any difference in the main chain or the side chain. So only if it is not structural, then you go for stereo. In structural, only if it is not chain isomer, then you go for positional isomer. This is the sequence, right? So it will have no difference in main or side chain. That means that will also be same. But what will be different? Different will be different in or difference in position of what all things are there in different position, different in positions of functional group or multiple bond or substituents. If these things are at different position, then we say that there is a positional isomer. And now if you see the name, IUPAC name, so 2-degree prefix, that is secondary prefix, primary prefix, root word, and then the primary suffix and secondary suffix. So where do you see position? So positions are mentioned in, is 1-degree prefix has any position? Answer is no. Here you just have to mention cyclo or not. So there is no position here. There is no position in the root word as well. But there will be positions in 2-degree prefix, secondary prefix, location or position of multiple bonds, and the functional group. Right? This represents what? Substituents. This represents multiple bond, and this represents functional group. So positions will be mentioned here, and that's why they will be different. So that is what positional isomers are. Right? So you should be able to find out whether there are positional isomers or not. So if there is a chain isomerism possible, then that will be chain isomer, not positional isomer. If chain isomerism is not possible, then only you will go for positional isomers. That means positional isomers comes into picture only when the chain length is same. Sorry. Say for example, here, let's say there is a structure like this, OH. Not like this. Okay, and so if you see the main chain is 1, 2, 3, 4, and 5 carbon. This is not carbon. Similarly, here 1, 2, 3, 4, 5 carbon. So chain length is same. Even the functional group is same, right? But the position of functional group here and here it is at position 1, while in the second compound it is at position 2. This is an example of positional isomer. right? Now let's see whether you understood the concept of positional and chain isomers both or not. So this is structure 1, structure 2, and structure 3. So if I take pairs, right, say 1 and 2, and 1 and 3, and 2 and 3. These are the 3 different pairs I can form out of this. So now can you tell me 1 and 2, is it positional, chain? Which type of isomer is this? And one more thing, before moving to find out whether isomerism is possible or not and which type of isomerism is there, first you need to verify that the compounds have same molecular formula. If the molecular formula itself is different, then there is no question of isomerism. Then there are 2 different molecular formulas. So one thing is clear, there is C5 here, here 1, 2, 3, 4, 5. So this is also C5, 1, 2, 3, 4, and there is one more carbon here. So this is also C5. Coming to number of hydrogens, 3, 2, 2, 0, and 3. Right? So 3 plus 3, so this is C5H10. Coming to number of hydrogen here, 3, 2, 2, 3. This is also H10. Here, 3, 3, 1, 3. So 3 into 3, 9 plus 1, 10. So this is also H10. And there is only one oxygen next door. So oxygen, oxygen, oxygen. So you can see that all of them have same molecular formula. So if the molecular formula is same, then only we go for isomerism. Now you have to decide which type of isomerism. So if you take 1 and 2, which type of isomerism is this?
Positional.
This is positional. The main chain length is same, 5, and only the position of double bond O is different. 1 and 3.
Yeah. 1 is positional, 3 is chain.
Wait. See, isomerism involves 2 structure, right? See, it 1 and 2 together, it's like if you have 2 siblings, right? Suppose
Okay, I think I understood.
you
We
understood, right?
compare both of them. Yeah, we
You-
compare 1 and 2 and 1 and 3.
When which type of isomers are they? It is not an individual molecule is never an isomer.
Okay,
2 molecules are
all
isomer.
right.
For example, 1 and 2 are isomer. Which type of isomer? Positional isomer. 1 and
The
3,
other one is chain. Oh, sorry.
this one is chain, correct? Because the number 1 structure has 5 carbon and number 3 structure has 4 carbon, correct? And same thing for the
Last one.
good. Okay, so you understood. So that was about positional and chain isomer. That is how you should identify. Now I'll also give you some random, just few more random structures, and let us see if you are able to identify or not. I think chain and position is easy, so I'll move to the next one. Okay, so this is the last topic for today. Then we'll study different types of other isomers in the next class. So next, as I said, is functional isomers. So I think you must have got the idea. It depends on the functional group. So structural isomers, which differ in chemical reaction. And why there will be difference in chemical reaction? Because they have different functional group. So that means formula will be same. Molecular formula will be same, but their chemical reaction will be different. That difference in chemical reaction will be due to the difference in functional group. One of the examples we have already seen, the example was with which we have actually started isomerism, CH3, CH2, OH. What is this? This is an alcohol. But CH3O, CH3, this is an ether. So what is the difference? The family itself is different. This is alcohol and this is ether. The family or the functional group itself is different, but the molecular formula is same. If you see the first one, this is C2H6O. Second one is also C2H6O. Molecular formula same, but family different. That is functional isomer. Another example, say CH3CH2 C double bond O H. Which family is this? Which functional group is there?
Aldehyde.
This is an aldehyde. And now if I have CH3 C double bond O CH3,
Oh,
this is ketone. So two different functional groups, two different families. But if you see the formula, there are 3 carbons, there are 6 hydrogen and a oxygen. So same molecular formula, but two different structures having two different functional groups. This is what is functional isomer. Right? So now in how many forms you will see these functional isomers in your syllabus. So there will be isomeric alcohol and phenol. So alcohol and phenol. So having same formula but different functional group. What does that mean? See, alcohol, we know alcohol is like this. The carbon to which OH is attached is a carbon having sp3 hybridization. That means all single bond. While in phenol, what do you observe? You will have this. This is phenol. These two are not isomers. In this case, you will find isomers. Right? What is that? This is not the example. The example is now here of this case. What do I mean? Say a compound like this and another compound or molecule is like this, CH2OH. Okay, can you tell me the molecular formula of both? Are they different? Are they same? What is the molecular formula of both? Can you find out that?
yeah. Molecular formula. So this is 6 ring. Both are 6 ring. They have 3 double bonds.
6 carbon or 7 carbon?
Total there's 7 carbon.
Yes. So
In the ring there's 6.
yeah, molecular formula will have the total number of molecules. You can see
It's the same molecular formula.
it is same molecular formula. So number of hydrogen atoms.
There are let me count.
Okay. See, 1 here, 2,
2,
3, 4.
1.
Here there used to be, I mean, here there was one H that was removed and OH came. So this is 1. So 1, 2, 3, 4, 5 and 5 plus 3, 8. Right? Here 1, 2, 3, 4, 5, 6, 7, 8. So the molecular formulas are same. Now, are both of them alcohol, both of them phenol? My question is, are they functional isomer or positional isomer?
Oh,
Here you can see CH3 is here.
functional.
These are
functional.
functional. So functional isomers have higher preference. What we see here is this is a phenol because OH is attached to the carbon, which is having a double bond. This, while here OH is attached to a carbon, which does not have a double bond. So this is alcohol. Is it clear how one of them is while the other is alcohol? So that's why this is a category. This is a category of this is a situation in which you will find a functional isomer. That is when you have alcohol and phenol. This is one such example. Some very common examples are something which we have already seen. These two we have already seen, but these are some special cases where you will find if you don't study it now and if it comes in your exam all of a sudden, you may miss this, right? So that is the example of isomeric alcohol and phenol, right? Similarly, the second category, which and special category is ring and chain isomers, right? These are not different types of isomers. These are types of functional isomers. These are different cases of functional isomers. And even this is very simple to explain. Let's see this compound. What will be the molecular formula? You can see there is only carbon and hydrogen. So the molecular formula for this compound will be C4. No doubt in that. How many hydrogen? 2 plus 2 plus 2 plus 2. C4H8. Is that right?
Yes.
Okay. And what if the structure is like this? So again here you have 1, 2, 3 and 4 carbons. So that is C4. How many hydrogens? 3.
So plus 2 plus 1 plus 1, which is 7.
Here there are 2.
So 8.
That is C4H8, right? So we will see more examples of, we will see more such examples later. For the time being, that's all for today. And I'll see if I can record a video and I'll send you. I'll try to finish this isomerism and you also try to go through the videos before the next class. So I'll try to cover all the types of functional isomers in that.
Okay.
Okay. Okay. So that's all for today.
All right. Thank you, sir.
Thank you.